In this software development example, I will show you how simulation can be used in project management. A software development project consists of 6 activities. The completion time of each activity has been estimated. Based on the past experience, we have the minimum, maximum, and the most likely completion time of each activity. For example, for activity E, implementation, in the best case scenario, it would take 3 months, and 7 months in the worst case scenario, but most likely it would take 5 months. The last column F also indicates that activity E has predecessors B and C, which means we can only start working on E after we complete both B and C. This information complicates the simulation. The amount of time it takes to complete each activity is random. We are asked to find the expected or average duration of the entire project. This diagram shows the relationship between the activities. The first checkpoint on the far left is the starting time, time 0. At time 0, we can only start working on activity A because all other activities have at least one predecessor. Using the most likely completion time information in column B, we know A would take around 3 months to complete, and we arrived at second time checkpoint. By now, it's probably in month 3. We can start working on activities B, C, D because all of them require a predecessor of A, which we have just completed. Again, using the most likely completion time information in column D, we know that activity D would take the longest to complete because it takes 12 months to complete D, while it only takes 3 months to complete C. Once we complete both B and C, we are at the third checkpoint. By now, it's in month 10 because it takes 7 months to complete B, and we have to complete both B and C before we can arrive at a third checkpoint. We can now start working on E, which requires the completion of both B and C. Using the same kind of strategy, we can fill in the rest of the diagram. From the second checkpoint to the fifth checkpoint, which is also the last checkpoint, it would take 16 minus 3, that's 13 months to complete. During this 13 months, we should be able to complete activity D, which usually takes about 12 months to complete. It is also interesting to realize that both activities C and D are not very crucial here, as a short delay in these activities would not result in a change in the total completion of the entire project. Regarding the elements of the business simulation, the duration of each activity is clearly the probabilistic inputs that we have to generate. Once we know the completion time of each activity, we can compute the total completion time of the entire project using this diagram. But how do we generate these probabilistic inputs? Using the minimum, maximum, and most likely information for each activity, we can use the risk PERT and risk triangle functions to generate the duration of each of the 6 activities. Both risk PERT and risk triangle takes 3 arguments. The first argument is minimum, the second is most likely, and the very last one is maximum. Strictly speaking, the risk PERT and the risk triangle are 2 different kinds of random number generators. But for our class, we make no distinction between the 2 and use them interchangeably. To simulate the duration of these 6 activities, we use risk triangle function as shown in column B. On the right-hand side, we have time to reach at each node or each checkpoint. For example, at node 1, the time reached is 0 because that's the starting time point. At time 2, we have completed activity A, that's cell B12 here, so that's why we put a B12 here. At node 3, we have completed both B and C. It took us B13 amount of time to complete B, and B 14 amount of time to complete C. To move from node 2 to node 3, it would take us the maximum of B13 and B14, so we use max function here. To calculate the time reached at node 3, we also need to add the time reached at node 2, that's F13. At the very last step, node 5, there are two paths to reach node 5. One path is through the completion of activity F, and the other one is through the completion of activity D. The maximum of these two times is the total completion time of the project, as we can see here. So clearly, cell F16, that's this one here, should be defined as the output when we run at-risk simulations. We choose 1,000 iterations to simulate 1,000 software development projects. Note that this particular simulation is quite time-consuming. Here is the summary of the simulation based on those 1,000 iterations. The average completion time is 16.69 months. It takes at least 14.17 months under the best condition, and at most 20.59 months at the worst conditions to complete the project. The 90% confidence interval of the completion time is 14.97 to 18.62. Half of the project were completed in less than 16.51 months. Along with other summary statistics, the simulation result provides us with many insights into how long our next project will take to complete. Let's look at a variation to this example. Suppose that 3 experts have expressed a different opinion on the most likely completion time of the activity E here. One expert believes that most likely duration is 4 months. The second one thinks it should be 5 months, while the last one thinks it should be 6 months. How sensitive is the total completion time of the project to the differences in their opinions? We could run the simulation model 3 times and use each expert opinion one at a time. This will do the trick, except that it becomes very difficult to compare the simulation results. The risk sim table allows us to combine the results from 3 different simulations into one. In cell D7, where the opinions are different, we enter the function risk sim table. The arguments of the risk sim table is the list of different opinions we have. They are 4, 5, 6. Because we are using a risk sim table here, we also need to change the number of simulations to 3 to match the number of arguments in the risk sim table. At risk will run 1,000 iterations using 4 for cell D7, and another 1,000 iterations using 5 for cell D7, and another 1,000 iterations using 6. Here are the combined simulation results using 3 different expert opinions. We could also choose to display individual simulation results by selecting Sim 1 or Sim 2. This allows us to have a side-by-side comparison to see how sensitive the project completion time is to expert opinions. When we use 7 from the last expert, that's green histograms here, the project completion time is longer than the completion time when the first expert's opinion of a 5 month is considered. As you can see, the average completion time for the last expert is about 17 months, whereas when we use the expert opinion from the first expert, it's only 16.37 months. This also concludes this video.